All right, hello everybody. My name is Kroer. I'm currently wrapping up a postdoc at Facebook Core Data Science, and then in the fall, I'll be starting in Columbia's IAOR department. This is joint work with my co-authors at Facebook, Alex Peysakhovich, Eric Sodomka, and Nico Stier. And I'm going to be talking about computing large market equilibria. So, what are markets? I'm sure we all kind of know. So, there are traditional markets, such as actual physical markets, or things like the stock market. In this talk, we're more interested in sort of more modern internet markets. So, for example, pricing items on Amazon, or pricing ads for Google searches, or when you open up your Facebook feed, or say, for example, pricing ride sharing. Okay? So the main question, of course, that what we're interested in is who gets what and why, right? And in this particular talk, we're going to focus on a very classical solution concept for that, which is the market equilibrium, okay? And in particular, we're going to focus on the Fisher market setting. So in the Fisher market setting, there are a bunch of buyers, each with some finite budget, and there's a bunch of items, each with some finite supply. Now, all of these buyers are going to have preferences over the items, and the items are going to have prices that we're going to get to choose. Given prices, each buyer is going to buy their favorite items given their budgets and based on the prices that we have decided on. And we're going to say that this is a demand of a buyer is a set of items that is optimal given the prices, okay? And what we're interested in is finding a market equilibrium, which is just a set of prices for the items such that supply equals demand if we give an allocation where every buyer gets an allocation that's in their demand set given the prices, okay? So why do we care about finding equilibria? One reason we might care, for example, at Facebook, is that it can let us make counterfactual predictions, okay? So under the sort of like somewhat reasonable assumption that working markets are going to find prices to set the supply equal to the demand, these kinds of equilibrium computations allow us to sort of ask counterfactual questions. So for example, if we have a Fisher market, but suddenly all of the supply of some subset of our items goes up drastically, how can we reason about how prices are going to be changing? And how can we reason about, say, the welfare properties of the market? Another reason we might care is actually even in markets where there aren't sort of intrinsically money involved, we might still care about market equilibria. So a very famous case for this is just for using market equilibria for allocation. So in that setting, we have a bunch of items, and we want to allocate them to people. And the question is, how should we do that? It turns out that one very reasonable way to do that is via something called competitive equilibrium from equal incomes. And in this idea, what we do is we ask everyone their preferences. Then we give everyone a budget of fake money. Or if there's real money in the market, then we can use real money, of course. If there's real money, then we're going to be dealing with quasi-linear preferences where the utility of agents are just the utility of the goods that they receive plus whatever money they have left over. Whereas in fake money markets, agents are just interested in the set of goods that they get, and so the money has no meaning beyond specifying how we arrive at an allocation. Now, what we do in this setting is we then just compute a market equilibrium, and then we give everyone the resulting allocation that came from it. And if we're using real money, then we then also charge them their prices. And if we're using fake money, then we just forget about the prices after that. And these kinds of ideas are used, for example, in matching MBAs to courses. And it's also used on split.com, for example, for matching roommates to chores. So those are two sort of applications for why we might care about this. In this particular talk, we're going to focus on the setting where all items are divisible. Now, we'll give a little bit of theory where this doesn't actually come up. But for all of our experiments, especially, we're going to focus on the divisible item setting. And this is sort of very reasonable, for example, for online ad markets, where you might think of items as sort of extremely large groups of impressions and stuff like that, okay? Secondly, we're going to assume that valuations are additive. So that just means that the utility of a buyer is just the inner product of their valuation vector times the allocation that we give them, okay? So why is CEI a good mechanism? So this is this competitive equilibrium from equal income. Well, it turns out, first off, it's envy-free. So if everyone has the same budget, then there's no envy. If they don't have the same budget, then it's envy-free up to a rescaling relative to the budget changes between people. It has no regret in the sense that everyone is sort of doing the thing that is optimal given the prices we've specified. is also Pareto optimal, which means nobody can be made better off without making someone else worse off. And it turns out that it has actually pretty nice incentive properties in large-scale markets, even though it's not incentive compatible in the small-scale case. Okay? And it has sort of like this distributional fairness that results from the fact that the allocation of the market is actually the solution to this optimization problem that I'm giving here, which is to maximize the sum of the logs of the budget-weighted utilities of the agents, such that the allocation is feasible, which just means that it respects the supplies, okay? And it turns out these logs, they come from the fact that this is equivalent to maximizing the geometric mean of the utilities, okay? So what is the framework that we're working with? Let's talk about fake money markets first here. So again, like I said, in this setting, what we can do is we can compute equilibria via this optimization problem. Now, since this is an optimization problem, it turns out it's actually convex, so it can be solved in polynomial time, right? But in the types of settings that we're interested in, such as internet markets, that's not actually enough, because these markets are so large that standard convex optimization techniques are just not going to be able to be applied. In fact, most of the time, you can't even write down a primal solution because it's going to take up too much space on your hard drive. Okay? So instead, in this paper, we study the following alternative approach to this. You start with your original market, which is shown on the upper left, and let's say this is some very big, complicated market. Then you come up with some kind of abstraction of this market, which compresses it down to a simpler market that's easier to deal with. Usually this especially relates to dimensionality. Then you compute a market equilibrium in this smaller abstracted market, and the resulting allocations and prices that you get in this abstraction, you lift back out into the original market and you use that as your solution, okay? So that's great. Of course, the big question is, how well does this work? And this is kind of inspired by a different line of work on solving extensive form games, where a similar approach to this was actually used for computing sort of better than human poker AIs. So it has worked really well in the context of extensive form games, and now we're sort of trying to look at how well can we use it here. Okay? So what are reasons why we might care about this market compression? Well, there's actually also another reason, which is that in many real-world settings, not only is the market extremely large, we might not even know the complete market. We might only have some observations from the valuation matrix in the market, and then we have a bunch of question marks where we have to make some kind of inference about what the actual valuations are. Now, the standard approach here, as I'm sure everybody knows, is to do matrix completion, right? And so the assumption there is that the real market somehow has a low-rank structure, and if it has a low-rank structure, then we can just do matrix completion, and we actually get a good approximation to the original valuation matrix, okay? So basically, the approach there will be we just fill in with a low-rank approximation, and we solve for that approximation, and then the question is, how good is that going to be relative to some potentially different but similar, if the market is indeed low-rank, matrix, okay? And so the key assumption there is, again, we assume that the market is low rank, and that means that buyers and items can be represented by some low-rank d-dimensional vector, where d is much, much smaller than the number of buyers and the number of items, okay? And we approximate Vij, which is buyer i's value for item j, by some vector representation of buyer I and item j in this space. So, and then the value is just the inner product, okay? And like I mentioned, this is the standard way of doing sort of recommender systems. For example, if you have the Netflix challenge and stuff like that, right? So how do we learn these vectors? We just do this with sort of standard approaches. So you have some set of observed entries, and you just compute some low-rank representation so that you minimize sort of this L-squared error plus some regularization term. And you can do that with sort of standard projected gradient descent methods. And now we have estimates of unseen values. So that's great, right? Now, the second part is, okay, so now we filled in our matrix, but it's still so large that we can't actually run our convex program on it. So the second thing that we do is that we compute a smaller representative market abstraction, okay? And the way that we do that is, I'll start by showing how we could get representative buyers, and getting representative items will be analogous. we take all of the buyer vectors, and then basically what we do is we compute a k-means clustering of the consisting of m clusters, and then for each cluster of buyers, we use the centroid of that cluster as a representative agent for that cluster of buyers. And that representative agent is then assigned a budget that's equal to the sum of the budgets of all the buyers in the cluster, okay? And then we do the same for items, right? So we just cluster all the items using these low-rank representations. And the supply of each representative item then is just the sum of supplies of all of the items that are belonging to that cluster, okay? Okay, so now we have representative buyers and we have representative items. So how do we have valuations in this space? Well, because we just use the centroid of each of the clusters as the representative vector, and we just set the valuation equal to the inner product of the centroid of a given representative buyer with the centroid of a given representative item, okay? And here I'm just, in the plot, I'm just showing sort of an example of how we might do this, right? And here, for example, we've constructed 3 representative, say, buyers, each of which represents a large number of sort of individual data points. Okay? So now, of course, the representative market that we get is just equal to, the size of it is just equal to the number of clusters of buyers that we have times the number of clusters of items that we have. And ideally, this is going to be much, much smaller than the original market, right? Okay, so like I said earlier, what we do once we have this representation is we compute a market equilibrium in this abstraction. But once we have this market equilibrium, we have to actually project that solution back out into the original space, right? So how do we do that? For each item, it's very simple. All of the items are just given the same price as the representative item that they're mapped to, okay? For buyers, it's slightly more involved. So for each buyer, they, remember, are assigned to some representative cluster. And that representative cluster has some allocation in the abstraction. What we do, one version, is to just do a proportional lift, right? So for all of the buyers in a given cluster, each buyer in that cluster just gets the fraction of items assigned to the cluster corresponding to their contribution to the budget of the representative agent for that cluster, okay? And it turns out that you can kind of think of this as an equilibrium in the original setting, except that now it's with respect to a different valuation matrix, where every buyer has basically been replaced by their abstracted valuation vector, okay? A second approach that you can use, which is sort of slightly smarter, is once you've computed your abstracted solution, instead of doing this proportional allocation, what you can do is for each of the representative buyers, we can actually compute sort of recursively another market equilibrium just within each of the buyer clusters. And so what we do is we take each of the clusters, we take all of the items that were assigned to that cluster, and then we compute a market equilibrium just for that sub-instance corresponding to that cluster. Now, if you do that, it turns out you get sort of weakly better properties in terms of some of these metrics that we care about, such as, say, the nearness to Pareto optimality and regret and so on, okay? So we give some relatively simple theoretical results when you do this. So it turns out you can think of all of what I just said as basically computing a solution to this convex program that I mentioned earlier using a new matrix V hat that's different from the original matrix V, okay? So V hat is basically going to somehow represent the values of the agents that resulted from doing all this clustering and low-rank approximation. Now, if you do that, basically you can show very easily that things like envy, regret, the proportion of the maximum share that's maintained is all bounded additively by the matrix norm distance between V and this new matrix V hat that we've constructed. Furthermore, you can also show that the optimality gap for the Nash social welfare is bounded multiplicatively, okay? Furthermore, we can also show that this recursive lift that I mentioned, which is sort of slightly smarter than the proportional lift, leads to weakly better Pareto gap regret as well as maximum share. Unfortunately, it might lead to worse envy on the other hand. Finally, if you sort of use a standard first-order methods approach to computing your market equilibrium, then the speed up that you get from this compared to just running your convex program on the original problem is on the order of alpha to the 3/5 times beta squared, where alpha is the fraction of bidders that you have in your representative problem as compared to in the original problem, and similarly, beta represents how much smaller the number of items is in the abstraction versus in the original problem, okay? So this is just in terms of the worst time convergence, though. In practice, you know, these worst case bounds usually aren't too tight, okay? So finally, we ran a whole bunch of experiments with this to look at how well does this actually perform in practice, okay? And so these experiments were conducted on 2 data sets. There's a third one, which I'm not gonna cover here because I'm gonna run out of time. So the first data set, which I think might also be of independent interest, is one that we collected. And what we did was we went on Amazon Turk, and we created a data set which consists of 50 household items that were sort of the top reviewed items from Wirecutter. And then we asked about 3,000 individuals to enter their willingness to pay for these 50 items, okay? The nice thing about that is that we have a complete data set where we got valuations for everything. Of course, there are some zeros and so on. And then finally, we also did some checks to see whether it seemed reasonable. So at the end, people were asked, did they actually feel like they could give reasonable valuations for the items and so on. So that's one data set. That one is quite hard to deal with because we didn't have very many categories of items. Instead, we have like one item that corresponds to having a dog, for example, and stuff like that. So anyway, if anyone's interested in this data set, we can also share that. Secondly, we used the movie lens data set, which is much bigger. We extracted a submatrix consisting of 6,000 individuals that rated about 4,000 movies. Now, for this data set, we do have incomplete data, and so we fill it in using this low rank approach that I talked about, okay? And so the empirical question that we're asking is, if we use this low rank approximation, plus we do this clustering in order to arrive at a representative market, how well do we maintain sort of these efficiency, national social welfare, regret, et cetera, optimality guarantees that the original market equilibrium approach has? And it turns out that you can actually do pretty well. I'm running out of time, so I'm gonna have to blaze through these results a little bit. I'll just try to give the high-level takeaway. So for the household items data set, which is quite hard of an instance in the sense that we have many buyers but not that many items, we find that you can sort of get a reduction in instance size of maybe, let's say if you increase your instance size by a factor of 100, you get like a 10% loss or so in a lot of these metrics. On the other hand, on the movie lens data set, we actually do much better. So in the movie lens data set, it's much, much larger. There's many items and many buyers, and so you would expect there to be sort of more low-rank structure that we could potentially exploit, right? In that data set, we actually do a 90% compression per side, and so there, we find actually that you have relatively small error even when you have sort of like a large amount of abstraction, okay? So in conclusion, abstracted equilibria turn out to have pretty good properties. Now, this is more so for markets that have sort of like lots of low-rank structure, and we can see that in the data. So I'll just leave the conclusions here because I'm out of time. Here's my website and my email. You can find all of these papers on my website as well as on arXiv. And of course, I'm also happy to take questions. Thank you. I don't think that it would actually change things all that much in the sense that for these Fisher markets, if you want to take quasi-linear utilities into account, it turns out like the convex program stays largely the same. You just have basically you add an extra constraint to the dual, as it turns out. But apart from that, it's actually very similar, and you can even kind of think of the real money as another item in a market in the sense. And so, the objective function? Well, the national social welfare Yep. No, I mean, the objective basically stays the same if you add quasi-linear utilities, right? So if you look at the primal convex program, when you change the quasi-linear setting, you just get utilities where you have a further term for the leftover money. And then you do have sort of a one linear term on the outside. But apart from that, it basically stays the same.